Hello students, in this video we are going to answer this question: apply Gauss law to calculate the electric field due to infinite plane sheet of charge. This was asked in 2014 AHSEC final examination under Assam Higher Secondary Education Council. And before we start, please subscribe the channel and hit the thumbs up button. Also share with your friends, okay? And don't forget to hit the bell icon, right? And please support me to grow my channel, inspire me to create new contents for you, right? So now let's start. So here you see apply Gauss law to calculate the electric field due to an infinite plane sheet of charge. So what was the Gauss law? Suppose if a closed surface encloses a q charge in it, then flux through this surface is given by q by epsilon naught, right? This was the Gauss law. So here we need to find the electric field due to a plane sheet. Suppose we have a plane sheet which is charged, uniformly charged, and this is infinite plane sheet. Okay, this is infinite plane sheet. Let me consider this is positively charged. This is uniformly charged. Surface charge density is suppose sigma here. So now in order to find the electric field due to this plane sheet, let me imagine a Gaussian surface. So cylindrical Gaussian surface like this. So let me consider this is the Gaussian surface, cylindrical Gaussian surface, and the length of the Gaussian surface is same in both ways, right? On the left hand side as well as on the right hand side. Okay, so and let me assume this Gauss surface such a way that half of the Gauss surface is on this way and half on the other way, on the other side. Okay. So now what happens, as this is positively charged, so electric field, direction of electric field at this end should be in this direction. And let me consider this area, very small area element ds here. Okay, ds. So and the area vector is perpendicular to the surface, that's why its direction will be also in the direction of the electric field. And similarly at this end here also, the direction of the electric field, that should be away from the positive charge, so that should be in this direction. This is the electric field, and the direction of the area vector should be in the same direction, as it must be normal to the surface, right? So this is the ds vector. And for the curved surface, for this curved surface, right? So here you see the direction of the area vector will be normal to this curved surface, right? Normal to this curved surface. So let me take this as n cap. Okay, so which must be perpendicular to the direction of electric field, which is perpendicular to the direction of electric field, because direction of electric field is in this direction. Here you can see in this direction, right? So now first let me write what I have considered. So let us consider a thin infinite plane sheet which is uniformly charged with charge density sigma. Let me consider sigma is the charge density of the sheet. Okay, now suppose we are to find electric field due to, so electric field, let me consider that E, this vector, is the electric field due to the infinite sheet. Right, infinite sheet. Okay. Now let us assume a Gaussian surface that should be cylindrical. Cylindrical Gaussian surface of length twice r. So let me write within the bracket r on each side. Okay, r on each side of the sheet. So let me take that way. Right now, here let me use numbers for the surfaces. Okay, let me take this surface as number 1. This one here you can see this surface is suppose surface number 1, and this surface is suppose surface number 2. So let me write here, this is 2, this is suppose surface number 1, and curved surface is suppose surface number 3. Let me use that. Okay, so 1 and 2 I have taken in surfaces, and 3 is the curved surface. Okay, let me write here one more thing. Sheet, electric field due to the infinite sheet at the point P, suppose. So we are to find the electric field at this point. Suppose here is the point A. So let me write it, draw it clearly. This is the point P. Suppose this is the point P. Here we are to find the electric field, right? At point P. This is the point. This is the proper diagram. Here is the point P. This is the direction of electric field, which is in the outward direction, away from the positive charge, right? And the direction of the area vector, this is a very small area suppose, and the area vector which must be the perpendicular to the area. This is the direction of the area vector. So on the curved surface, the area vector should be perpendicular. Here this is the direction of unit vector of the area vector of the curved surface at this point, and here is the direction of electric field. So angle between them is 90 degree, and here you see in this at this end. So direction of electric field and area vector ds is also same again here, right? So this is the diagram, proper diagram. Just draw the diagram from here, that will be better. Okay, so let me let me use numbers for the surfaces. This is number 1, surface number 1, and the curved surface is suppose number 3, and I have made this end number 2, right? And the area of cross section of this cylinder, the cylindrical Gaussian surface, I have taken as S. Okay, so take this draw this diagram. Okay, so now let's continue. Okay, so hope you got it. This is the point P, right? And so let's continue. Okay, let me go to a new slide. Just take a screenshot. So here you see this was the diagram. So according to Gauss law, flux through any surface, that is phi, that must be equal to the charge enclosed by the Gaussian surface divided by epsilon naught. And here the charge enclosed is, so here you see if we consider this area of cross section is suppose S, this area of cross section is suppose S. Okay, let me consider this is S. S be the area of cross section of this Gaussian surface, and the charge per unit area is sigma. So that's why. So charge enclosed by this Gaussian surface, that's going to be the charge on this area, right? So that should be sigma into S divided by epsilon naught, where S is the area of cross section of the Gaussian surface, area of the cross section of the Gaussian surface. Right, so that's what we have taken. Now we know flux through a surface also can be calculated like this: total flux through the surface is also can be calculated. Phi is equal to integration, surface integral E dot ds, right? E dot ds. So here you see E dot ds, in this case surface integral of E dot ds, it can be written as here we have considered three surfaces. So what are those? This end is taken as surface number 2, and this end here you can say this end is taken as surface number 1, right? And this curved surface is taken as surface number 3, right? So hope you have understood this. So what we can do here, just wait, sorry for this displacement. Okay, so now, so for the first surface E dot ds, that should be E ds cos theta here. For the first surface theta is 0, because here you can see this is the direction of electric field as well as the direction of the area vector as well. Okay, for this end you can see the direction of the surface area vector as well as the electric field are in the same direction, because electric field should be away from the positive charge, right? That should be in outward direction, right? So hope you have understood this. So now you see, so that's why the angle is 0 degree here, cos 0 degree. Similarly for surface number 2, for this surface number 2, this end, which is also surface area of S, so here area vector is also in the same direction as E. This is the direction of area vector as well as electric field. So that's why here also theta is 0. So E dot ds, so that is E ds cos theta, that is cos 0 here. Let me use the red one here. E ds cos 0 degree, and plus here you see, and the third surface, in this case the area vector which is perpendicular to the curved surface, right, that is n cap, which is the unit vector along the area vector of the curved surface at this particular point, at this point, suppose at this particular point. So the electric field is in this direction, so this is 90 degree, right? So hope you have understood this. So that's why here we're going to write E ds cos 90, and cos 90 we know equal to 0, so that's why this part becomes 0. So we have, so integration E is constant in both, so as we have taken this, both ends are at the same distance from the seat. So here we can take E is fixed for both. So E is taken outside the integral, surface integral. So for surface number 1 and surface number 2, and this is 0, which is not necessarily to be written. So phi, and this phi is nothing but according to Gauss law, this, right? So let me use this as equation number 1 here, sigma s divided by epsilon naught. So here we can write using 1. So now what we can do here, you see integration of ds, which is nothing but very small area element we have considered here. Okay, very small area element we have considered here, ds, right? So if you integrate it, then you're gonna get the complete surface of area of cross section, right? So that's why here we are to get sigma. Sorry, let me write here sigma ds by epsilon naught e into s. If you integrate ds, you're gonna get s, which is the area of cross section. So e, again if you integrate this, then also you're gonna have the same area, es. So it implies es 2es is equal to sigma s by epsilon naught. So here you can see clearly s cancels, so that's why E is equal to sigma by 2 epsilon naught, right? So sigma by 2 epsilon naught, and this is the electric field due to infinite plane sheet. So hope you have understood this. Thank you for watching. See you in the next video. Do subscribe my channel, support me to grow my channel, inspire me to create new content for you, right? See you in the next video. Bye bye.